A very good morning to one and all present here. I am Palak Kothari, a team member of Astronomy Club of Government College of Engineering, Nagpur. It gives me immense pleasure to grace your presence in the inaugural session of third edition of Stargaze, the Astronomical Workshop, as a part of Adjunct, the annual technical fest of Government College of Engineering, Nagpur. Here's a hearty welcome, big and warm enough to encompass you all. To say we are thrilled to see you is an understatement. Before we begin with this session, I would like to express my heartfelt so sorry, my connect. Before we begin with this session, I would like to express my heartfelt gratitude to all of you who sincerely committed to this event to make it a success. The world is full of diamonds and gems, and we are having some of here today to build this event. I would like to give my heartiest welcome to our guest speaker, Professor Ashish Mahabal, sir, an astronomer and lead computational scientist at the California Institute of Technology in Pasadena, California, Mr. Malhar Kendurkar, sir, an observational astrophysics researcher based in Prince George, BC, Canada, Dr. M.B. Kumtekar, sir, professor and head of Civil Department, Government College of Engineering, Karad, under whose able leadership as then the principal of Government College of Engineering, Nagpur, the Astronomy Club was formed in February 2017. Our honorable principal, Dr. N.D. Gavgave, sir, Dr. P.R. Deshmukh, sir, Head of Department of Electrical and Electronics and Telecommunication Department and Conveyor of Adhyay, Dr. J.B. Randhawa, ma'am, the faculty in charge of Astronomy Club of Government College of Engineering, Nagpur, all the faculty members, and a hearty welcome to you all. We need your constant support to make this event a huge success. Before we begin with the session, I would like to request our Honorable Principal, Dr. N.D. Gavgave, sir, to say a few words on this occasion. Over to you, sir.
Yeah, very good morning and warm welcome to one and all. It's my pleasure to be here at this workshop, Stargaze, organized by Astronomy Club of Government College of Engineering, Nagpur. Honorable ex-principal Dr. M.B. Kumtekar, who is the founder and pioneer of this Astronomy Club. Professor Ashish Mahabal, the guest speaker for today's workshop. Another guest speaker, Mr. Malhar Kendurkar, sir. Dr. J.B. Randhawa, Faculty Coordinator of Astronomy Club. Dr. P.R. Deshmukh, Convener of Adhyay 2021. All the student coordinators and dear participants. Astronomy Club, as it is mentioned that it was established in 2016, and I still remember the first event was organized by this Astronomy Club, and the same guest speaker, Ashish Mahabal, sir, was invited for that event. Today again we have an opportunity to listen him, to understand the various concepts as regards to the inventions which are being taken place as regards to astronomy. I'm really happy to be with you at this inaugural function of this workshop. Friends, we know all over the world the scientists are trying to explore the universe, and study of astronomy is one step to go for it. And I'm sure our young students, the future scientists, will be getting enlightened and some knowledge from the expert speakers. Without taking your much more time, I wish you all the best. Thank you very much for inviting me over here. Over to you, Palla. Thank you very much.
Thank you so much, sir, for your kind and encouraging words. Now, I would like to invite our beloved Dr. M.V. Kumtekar, sir, to express himself on this occasion. Over to you, sir.
Good morning. Hope I am audible. Please confirm.
Good morning, sir. Morning, sir.
Yes,
Very good
yes,
morning.
sir, yes, sir.
Honorable Principal and my friend Dr. Nitin, Dr. P.R. Deshmukh, the person, very strong person behind that Adhyay family, Dr. Randhawa, the faculty coordinator for Astronomy Club since inception, Honorable guest Dr. Ashish Mahabal, who is always supporting the Astronomy Club since inception, and today the guest speaker, Professor Mr. Malhar Kendurkar, all the faculty members, deans, heads of the department, and the delegates for this particular Stargaze program. In fact, let me at the outset thank Dr. Gaugave, Dr. Deshmukh, and Dr. Randhawa, and also the organizers of this Astronomy Club for again giving me the nostalgic feeling, as I was associated with this particular club since inception. And I have seen the development of this particular club right from 2017, when I really recall one fine morning, the first coordinator has come to me asking for a small telescope, which was difficult at that particular time. And then with that particular small thing, Rohit, I remember his name also, under the able leadership of Dr. Randhawa, so many programs were arranged, which in fact the astronomy is basically a field where people slightly stay away due to its complexity and some type of the, say the phobia or some type of the thing associated with it. But nowadays, to be honest with you, my dear friends, that direction or that dimension of the space has to be also thought of, even in the case of what is called as your say dwelling, because now the moon is not far off from us. Many of the programs and many of the events have been planned by the different countries, and it is not that the day is not far off when the people will think of staying on the moon, as there is no space left on this mother earth. We are now trying to go to the various, say, the planets, including the Mars and so many other issues. And basically the people are now out of the fear that these particular, say, the planets are going to turn your life. And from that particular point of view, I really congratulate the team and wonderful support by Dr. Nitin and also by Professor Deshmukh, and wonderful support, wonderful, I say, the backbone, Dr. Randhawa and her team, who are doing this type of the events. I'm really thankful to Dr. Ashish Mahabal, who is also supporting our club since inception and giving the more direction and dimensions to our students. I'm very much thankful to Mr. Malhar Kendurkar for providing his expertise and also to clear the doubts about this astronomy and definitely the world which is really behind what we can see in today's event. I wish you all the very best of luck, and I'm sure this type of the activities will be regularly conducted at Government College of Engineering Nagpur, which is one of the most promising institute from Maharashtra. Thank you once again for giving me opportunity and wish you very best of luck. Thank you.
Thank you so much, sir, for putting us out in this third. I would like to now invite Dr. P.R. Deshmukh, sir, to say a few words on this occasion. Over to you, sir.
Good morning, everybody. Honorable Dr. Gaugave, sir, Principal, Government College of Engineering, Nagpur. Dr. M.B. Kumtekar, sir, Professor and Head, Civil Engineering Department, Government College of Engineering, Karad. Dr. Randhawa, Madam, Faculty Coordinator for Astronomy Club. Today's honorable speakers, Dr. Ashish Mahabal, sir, Senior Lead Computational Scientist. Another speaker, Dr. Malhar Kendurkar, sirs. So on the behalf of Government College of Engineering, I welcome all of you in these today's astronomy workshops. First, I congratulate astronomy clubs to have this type of workshops which promotes the novel thinking towards the star. So it enhances the strengthens the activity related to star astronomy. So it is this speaker is going to be focused on the insights of the star astronomy. So this workshop is aimed at the teaching you about the movements of star and the working of the universe. So at the end, without wasting time, I wish you all the best for this today's workshop. So thank you very much.
Thank you so much, sir, for your kind and encouraging words. I feel very privileged to introduce you all to our guest speaker, Professor Ashish Mahabal. He is an astronomer and lead computational scientist at California Institute of Technology in Pasadena, California, where he leads the machine learning group for Zwicky Transient Facility. He also works on the methodology transfer between physical sciences and biological sciences. He is also an adjunct faculty at the Inter-University Center for Astronomy and Astrophysics in Pune, where he got his PhD in 1998. He will be talking to us about a few citizen science projects in astronomy and show how those with and without expertise can get involved at different levels and help drive the science. Beautiful thing about learning is that no one can take it away from you. With this note, I would like to hand over the stage to Professor Ashish Mahabal, sir. Over to you, sir.
Thank you so much for the warm welcome. And can you hear me?
Yes, sir.
Great. Okay, I'm going to share my screen. So once I find, okay, you should let me know if you can see. I need to make it full screen. Give me 1 second. Okay, can you see full screen now?
Yes, sir.
Excellent. Okay. So thank you for the very warm welcome again. And it would have been great to be in the same room and talking to you all and be able to do actual demo, for instance, and so on. But conditions are such that we cannot do that, so we'll do the best that we can. So I think you're not seeing the full screen now, are you?
No, sir.
I think it's the annotation program that someone started that brought it out of this. Okay, let me try again. My keyboard seems to have vanished. Give me 1 second.
Yes, sir.
Okay. I hope it'll stay that way. Right. So what I'm going to talk to you today about is contributing to astronomy as citizen scientists and enthusiasts. So one can come into astronomy at any level and be able to do something interesting and important. So you should stop me if there are any doubts or wherever you want to. I'll try to go slow in general. But what I want to do mainly is to make this interactive if possible, even if we are not meeting together, because there are many nuances to this, and I would like greater participation if possible. So I'll be talking in introducing how astronomy changed, and then be able to tell you about ZTF and then get on to the citizen science part. So let me tell you about the journey of astronomy, how it has been changing over the last several decades. So long back, several thousand years back, people were able to identify that there are constellations and then there are seasons. Again, I think this got out of the sharing has stopped, right?
Yes, sir.
So it's happening automatically. Shall I try to get out of WebEx and try to come back in?
I think that would be appropriate, I guess, because it actually booted me out once.
Oh, okay. So let me try doing that. So I'll join again in a minute. Try to stop Keynote and restart it in case there was any issue with that. Sorry about that. Yeah, this is what happens when we are doing things remotely sometimes. Okay, and I'm going to try again to share. Okay, can you say this again?
Yes, sir.
Okay, sorry, hope it doesn't put me out again. So long back, people had identified constellations, they had identified what planets were and how the planets move in the background of stars. Stars go around the Earth, or so to speak, during the night. And then slowly it was discovered that there are patterns in the stars and so on. So the only things that would change at that time that one could see were things like supernovae that would happen once every few decades, etc. And then slowly what started happening is that by the time of Galileo, there was the telescope, so they could observe Jupiter and its moons. And then observations of the moon suggested that the moon seemed to be going around Jupiter. And slowly this knowledge was getting accumulated. And like many other things, what happened is that initially this development was slow, and then it really took off after telescopes came about. More and more people started observing things, and we started learning about all kinds of things about planets and stars and galaxies and so on. So then when institutes were formed, the way the astronomical science progressed was where people could propose observing specific types of galaxies or specific types of stars. And through those observations, the knowledge got pushed further and further. We started getting learning more and more about these things. And now, initially, it was just observations, because when you have observations, then what you can do is that you can find connectivity with different things. So we could say that there are stars of different colors, there are stars of different temperature, there are galaxies of different sizes, and so on. Then based on this, the analytical theories started coming in. So that can be various relationships were proposed, and then observations were taken, and using those observations, those relationships were proven. Things like the gravitational force, for instance, right? Meaning there are planets that go around the sun, so the Keplerian laws, etc. And that led to a lot of developments again. Much later, and only a few decades back, when we had computers and so on, then we could do simulations. So we could try to create observations. The one big difference with astronomy compared to other sciences is the fact that we cannot experiment with our apparatus, with the things that we want to study. We cannot take a star and say that let us increase the temperature of it by 100 degrees and see what happens, like we could do in physics or in chemistry laboratory, right? And so we have to depend on observations. But then one alternative to observations is being able to create models. The models are mathematical, saying that if you take so much hydrogen and pack it into such and such volume, what will happen? And then if one can simulate that actually bring particles into the a computer simulation and see what is going to happen with respect to that, then that's going to tell you as it evolves as to how the star may evolve. Now, if the model is correct, then we'll see something similar in the universe also. And if the model is not correct, we won't see the same thing. So then what we do is that we get the model to predict something, and then we try to observe that. And once you observe that, then that tells us whether our model was right or wrong. So we can have a course correction. And that is how there are many models proposed. And that is how science corrects itself. It's self-correcting. So no one takes anyone's word just because someone said that. So even very famous scientists, if they say something, they have to be able to prove that, or someone has to be able to prove what they have said. And that's the important thing. And that is how it should happen in every walk of life. So in science, we try to go along with that anyway. And then besides simulation, what started happening again a few decades ago are sky surveys. So rather than being able to observe only small parts of the sky, there were these telescopes with large fields which could observe large parts of the sky. And then simultaneously, you could observe many variable objects, many stars, and then you could do statistical studies of those. And that really changed the paradigm, because now what could happen, rather than having only focused observations, you could take lots of observations. And using those observations, you could also do data-driven things. That is, not just start from a hypothesis, but start from data and using the data build hypothesis. So that is how data-driven science was born. So what you have is that you can fuse data. You have an observatory in one place and another observatory observing in another wavelength. They take different data. You can bring them together, and then you can do lots of things with that. And that is how we came to the era of machine learning, which is what you see everywhere. And in astronomy, you have to do that because the data, the sky surveys are so big that individuals cannot look at that. So you get all those data and try to process that. So that started happening a lot. So this is how sky surveys look. We started going from snapshots to slow movies of the sky. So on the left, you see CRTS, the Catalina Real-Time Transient Survey, on which I was working earlier. And at the bottom, you see the Zwicky Transient Facility, on which I'm currently working. On the top right is the Gaia telescope, with which it is in the sky. So it's orbiting and taking very accurate observations of the sky. And at the bottom right is LSST, or the Rubin Observatory, which will start operating in 2 or 3 years from now. And these are all optical telescopes. I have not even touched radio or X-ray or LIGO or neutrinos. So those are completely different things, and all of those together can tell you a lot about the sky. So what I mean by slow movies is that earlier, as I said, you could take a single observation and try to do something with that. But now you can take repeated observations of the same part of the sky. But repeated is not the same as we take movies, because with CRTS, for instance, we would have about 100 observations in a couple of years, not more than that. With ZTF, we have a survey that's going on right now, which takes observations every other night. So every 2 nights, we have 1 point in data. And then because one part of the sky is visible only half the year, because otherwise it's in the direction of the sun for the rest of the time, we get about 100 observations in a filter for one part of the sky for the same object that is in 1 year. So that is how progress happens, though, because now essentially from single observations, we can build time series. And from the time series, we can ask various things like, what is the change that is happening? Is there periodicity in the observations and so on? And so for doing all this, then you need to be able to bring in interesting mathematics. But what I'm going to try to tell you is that now we need more and more machine learning. And for machine learning, what we need are good data sets. And one way to get good data sets are using through the help of citizen scientists also. And that is where you all can come in. So we have to do real-time data processing now, because as the data get taken, so every night from the Palomar Observatory, the Zwicky Transient Facility, we get about 1.4 terabytes of data. Again, let that sink in. So 1.4 terabyte of data every night. And all that data is processed in real time. So we look for transients, objects that are changing in brightness, and then announce those immediately. So there are websites where you can subscribe and you can get those things immediately. So earlier we used to have data sets. Now we really have data streams. So every night of the order of 100,000 objects that change in brightness are announced by ZTF. And so we have really gone from static sky to a dynamic sky. Things are really changing out there. Again, you don't see them with the eye, because with the eye you can only see up to 6th magnitude. So magnitude system, in case you don't know, is a logarithmic scale, and smaller numbers mean brighter objects. So this was formed using Vega and what one could see with naked eyes long back. So magnitude 1 object is 100 times fainter than magnitude 6 object. And magnitude 6 is roughly the faintest that you can see from a dark part of the Earth. But with something like ZTF, we can go about 15 magnitudes fainter than that, which means 100 times 100 times 100, because 5 magnitudes is 100. So we can go a million times fainter than what your eye can see with something like ZTF. And at that level, at that brightness limits, things are really dynamic. And we are able to capture about 100,000 of those changing objects every night. And then again, what has happened is that rather than archival data set, we can now do it in real time. I mentioned that we now get 1.4 terabyte of data every night from just ZTF. So when I was doing my PhD, I used to go to the Kavlur Observatory to get data. And there at that time, we had magnetic tapes, and one magnetic tape could hold 50 megabytes. So that was the largest set that we could have at that time. And 50 megabytes to 1.4 terabyte, where we are, right? Meaning, so 50 times 20 is 1000. That would take you to 1 gigabyte, and another 1000 will take you to a terabyte. So that's the change that has happened. The other thing that has happened is that we now have distributed resources. So there are archives in many places. You can bring those together and do lots and lots of things. So one thing that I'm going to emphasize here is that though we have a lot of data, though we are learning a lot from the data, expertise is still critical. So despite all the automation, it's not going to happen that good astronomers are someone who will not be needed. Good data scientists are someone who will not be needed. That is going to be needed everywhere. So that's going to be a currency that will always stay important. So keep that in mind. So this is what I briefly mentioned earlier. So instead of being into hypothesis driven science, where you make a hypothesis, then do an experiment, then do data analysis and understand what's happening, you can start with data and data sets, data streams. From that, you can do exploration, visualization, display things. You look for patterns. And then based on the patterns that you see, you can make hypotheses now. And that also leads to understanding. So these two approaches are obviously complementary. You cannot leave one and just do the other. But we are more and more moving towards the right-hand side here. And so let's think about some simple classification problems. So here is a part of the sky, an image that we took with the Palomar Quest Observatory long back. And so one can ask that, can we identify stars and galaxies in the picture? So what we have here, for instance, is a galaxy. Here is another galaxy. And everything that is fuzzy may be a galaxy here. This is a galaxy here. But everything that seems sharp is likely to be a star. This could be a galaxy. This is a galaxy here, right? But that's not the whole thing, right? When you start classifying, there are many other things that are in there. And you need to get a little bit into details to understand what kind of things those would be. So there can be CCD defects you need to get rid of. There are cosmic rays which are going through us all the time and going through the CCD, which are hitting that. There can be bleed trails. There can be satellite trails. Now, all these things are something that we don't really need, right? Those are not what we are looking. But there can also be hidden things in there. There can be asteroids in the picture that we are not initially looking for. In fact, this image was made with a composite of 15 images. It was not a solitary image. And in the different images that were taken within a few minutes of each other, there was an asteroid and it was slowly moving. And in fact, this is here. So these 4 points that you see, those are because of an asteroid. And so we found this post fact. Of course, we find the asteroids in real time all the time. But the main thing that I was saying is that when you are trying to do classification, then your interest may be in something, but there are lots of other things. And being able to find those things can be very, very interesting. So if you look at the entire sky, its variety is far more. Don't try to read everything here. That's not for that. But I just wanted to emphasize that how the number of things that are in here are really vast. So you have transient objects which change in brightness in a short amount of time. And within the transients, there are GRBs and tidal disruption events where a star has gotten too close to the center of the galaxy and the black hole near the center of the galaxy rips it apart, or kilonovae. Or within supernovae, there are many, many types. There are core collapse supernovae, supernova type 1A, superluminous supernovae, and what have you, right? And so even in variable stars, there are those with spots. And then we have been finding so many exoplanets now. So there are stars with planets around them and so on. And all those data are in many form available in the public domain. So you can have access to that without any problems. And if you form teams, then you can download many of these data sets. There are tools available. I'm going to tell you a little bit about that. But the citizen science part that I'm going to tell you about is where you don't even need to directly download the data set. You should be able to log in, and then the problems are set for you automatically, and you should be able to get in there and do lots of interesting things. So let me tell you a little bit about the Zwicky Transit Facility. The field of view for Zwicky Transit Facility is really large. It's 47 square degrees. And we go down to about 20.5 magnitudes. Our exposures are 30 seconds at a time, and we use G, R, and I filters. So these are just different parts of the wavelengths that we can use, because each of those filters tells us a different aspect of physics that is going on in those objects. And then we have a well-tested subtraction detection pipeline. We cover about 20,000 square degrees every 3 nights. In fact, now we have a part of that gets covered every 2 nights. So it's closer to 14,000 square degrees every 2 nights in G and R. So that's what I had said earlier, that every second night we can get to the same part of the sky. This is slightly older DR3 here. We already are on to DR5. Every 2 months now, we are releasing a new data release. So you can see here at the bottom left number, this is about 233 billion. And now it has gone to 4 times that in the last few months. So those are the number of detections. So that's how big the data set is. And within that, we have been doing a lot of classification. And then whatever interests you, you can try to get in and try to do things related to that. So this is the sky coverage of that. And those of you who are programming minded, there are APIs available. So you can directly query this data set and be able to get that. So if you're interested in a particular area of the sky, you can just go in and grab images from there. Or if not images, grab catalogs from there and do your own kind of visualizations. You can ask how many X kind of stars are there, how many Y kinds of stars are there exoplanets in there. So ZTF does not look for exoplanets, but we have locations for stars for which exoplanets have been found, and you can do other interesting things with that as well. So the alerts that ZTF releases are of this fashion. And again, there are servers where you can get alerts from too. So the image that you see on the left here is the typical 30-second image that we get. This is only a small section. This is not the full image, of course. By the way, the 47 square degree that I mentioned earlier, a good way to understand how big it is by considering how big the moon is. The moon is about half degree by half degree, which means that the area is roughly quarter square degree, and one image of ZTF is 47 square degree, which means that roughly 200 full moons can fit inside a single image. So that's how big the field of view is. So this is a small section around an object that seemed to have changed in brightness. This is a reference image, same part of the sky, but what we have done is that we took lots of past images and stacked them together so that we have a deeper image. We can see fainter objects in that. And then during part of the pipeline, we subtract this reference image from this new image. We normalize them so that they are roughly similar brightness. And then what that does is that if there is any interesting new object, then it won't be seen here. And then in the subtraction, that new object is seen. So this bright object is common here and here. And this clearly, this is brighter than this is because this is a deeper image. Similarly, this is a noisier single object. This is a better seen single object because again, it is a deeper image. But when you subtract this image from the left image, then this object stands out. And that is the object of interest here, because what has shown is that there was something not in the deep image, but there is something in the new image, which means that that is a transient, something interesting is happening. So this is small 63 by 63 image. And then this is a single image, but we have been observing the same part of the sky for a long time. So what we do is that we can build a time series for that. So this is the light curve that is shown here. So on the x-axis here are days, and on the y-axis it is brightness in magnitude. So these light curves represent how these objects are changing in brightness. And clearly, this has suddenly become brighter. The smaller numbers, if you remember, smaller magnitudes are brighter. So this has started becoming brighter here, and that is what we are seeing. So these alerts, along with the stamps and images, are served in our data set. And there is a 30-day window that we have here. We can also get forced photometry, etc. here. We have various other metadata available with that, which can be used for visualizations, etc. So we have been doing lots and lots of things with ZTF. And you can see in the tree here that how we look for transients in real time. And within the transients, there are extragalactic objects, and there are objects from within our solar system. We have a program that looks for comets, and there's another one that looks for streaks. These are the streaks from asteroids, for instance, right? And if you take an image for 30 seconds of the sky, we are tracking with the telescope. So the stars leave point-like images. But because asteroids are moving faster, then even when we track the stars, the asteroids leave streaks like these. So we look specifically for such streaks and are able to find them. Similarly, here is a new image, here is a reference image, and we have a program that looks for such fuzzy things. This is a comet that ZTF was able to find out. Or this is a T-SNE plot, a 2D plot of lots of different kinds of variable stars that we were able to plot. And here are some supernova spectra. The reason for me to show you this is that in a sky survey, one is not looking for something specific. There are all kinds of things there. And different groups are interested in different aspects of the science. So they, some of them are looking for these streaking asteroids, some of them are looking for comets, some of them are looking for variable stars, some of them are looking for supernova. And through our citizen science program, we put a large part of this data in the public domain that you can look at as well. And so internally, we do lots of machine learning. And the thing that I wanted to emphasize again is that for this machine learning, we get clean data sets. And cleaning the data sets, going from raw data to a data set on which you can apply machine learning is a non-trivial thing. So 90% of the job is in going from raw data to data that is ready for machine learning. And then because there are so many good libraries available, actually applying the machine learning is somewhat easy. You still need to know somewhat from the domain knowledge, etc. But that's the easier part, really. So there are lots of, I won't go into detail here, but there are many programs that are available. So here are more astronomy applications here. And we can come back to this if you have any questions later on. So I'm going to do a small segue into machine learning because we'll be coming back to that when we get to citizen science. So earlier what used to happen is that you could derive features and you use those features then to do classifications. But with something like deep learning, which I'm sure you have heard of, what is happening is that you can directly take images. And here I've shown an example of cats and dogs. So you can apply a deep learning program on cats and dogs to identify which is a picture of a cat and which is a picture of a dog, for instance. So it internally builds large number of features, in fact, millions of features. And in that very high dimensional space, it tries to identify the separating space between the two. And what that means is that there is some black boxiness there, and trying to come out of that, trying to understand why the classification is happening is an important thing in a science like astronomy. So for instance, if I were to show you something like this, a bird, right? Meaning, so you could maybe identify it from its legs, but clearly its beak is missing, which is an important thing. The eyes are missing, so you cannot see the color of them, etc. And so that is where features that are strange come into picture. And many times we have projects where you are asked to identify features of those kinds. So some of you may have seen this adversarial examples. On the left hand side, you got three images. There is a school bus, there is a quail, and there is a temple. And then what can be done? And a machine learning algorithm perfectly identifies them after training. But in the middle, what was done is it was figured out which of those pixels were critical for identifying the bus as a bus, the quail as a quail, and the temple as a temple. And then a subset of those were changed, very subtle changes, so that you get pictures that are seen on the right, which seem exactly like the ones on the left to the eye. But because of those subtle changes on which the machine learning was trained to look at them in a specific way, then the machine learning program started calling all these ostriches. Because what was done was that the way the pixels that were changed, so there was also a classifier that looked for ostriches, and whatever was important in the ostrich, only those pixels were taken and modified in the middle. So the machine learning algorithm started thinking that the pictures on the right are of an ostrich. So something like that can happen. So one has to have robust machine learning algorithms also. And for that, it becomes even more critical to get good data. And so now I come to the Zooniverse part, which is the citizen science aspect, where we have data sets out there which you can log into also. So zooniverse.org is the website, but then within that, there are many programs available, and not just of astronomy, but of biology and history and all kinds of things. Within that, I'll give you specific links for our astronomy program also. So here we give the same three images that you have seen before. There is the science image, there is the reference image, which is the deeper image, and the difference image, which is the difference between the two. And what we ask you to do is say whether the object in the middle that is seen here in the difference image, is it real or could it be bogus, or you're not sure. So if it's real, you'll click on real and go to done. If you think it's bogus, you'll click on bogus and go to done. And if you're not sure, click on skip and go to done. Now, what does one mean by bogus? Sometimes what can happen is that, as I mentioned before, there can be these CCD defects, or there can be the subtraction may not be very good. So that is what it could come to. And then once you click something as real, then another window comes up which asks you, what kind of real do you think it is? And of course, we have tutorials for all these kinds of things. So we'll be looking at that also. So in fact, what we could do is that maybe have a quick segue into looking at the Zooniverse website itself, and I can show you the tutorial and the field guide that we have there, and then we can come back to the talk again. So by the way, are there any questions so far? So,
Hello, sir.
yeah.
So my question is like, how would the James Webb Telescope change how observations are taken?
Well, it's going to be a telescope that will be in the sky like Hubble Space Telescope, but more advanced because it's going to be in more recent times from now. And so it's going to be more powerful that way. But what happens is that for most space-based telescopes, there are few moving parts there. And so its capabilities will be limited compared to what we have from the Earth. It will be taking observations from outside of the Earth's atmosphere. And that's why, of course, they are going to be very good observations in with some limited wavelengths compared to what we can do from Earth. So it's a completely different kind of thing, though, right? So let me try to get to the
Okay.
universe numbers. Okay, can you see my browser now?
Yes, sir.
Yes,
Okay.
Yes, sir.
Yeah. Okay. So what we have here is this is how the project that we have is Zwicky Quirky transients. And you see these three images here again, the science image, reference image, and difference image. And when you come to the website, this is what you are going to be able to see. And in addition, you have got a light curve here. And we have got two different filters, as I mentioned, G and R. So you see light curve in that. And so you have this additional information to ask yourself whether this object seems real or not. And when you come in first time, it's going to show you the tutorial, but you can access it at any time again. So when you go to the tutorial, it's telling you, for instance, that you're presented three panels in the top half from left to right. They contain science, reference, and difference images, etc. And you can continue here to, then it tells you what the light curve is, what that means, etc. And then it tells you that what kind of transients there are. This is a wonderful supernova, for instance. This is a galaxy. This is the reference image, and there's nothing here. And suddenly you find that there is something here one fine night in the difference image that really stands out. And so that is a supernova. So some examples related to that. Or this is an example of a bogus, for instance. So it just happened that the seeing was different. The astronomical observing conditions were different. And so both these objects, in fact, all three objects left something here. So not only do you see something in the middle, but you see something for these two stars too. That tells you very likely that all three of them are bogus in the sense that they are astronomical objects, but the difference is not because the object was brighter today. It's just because of things. So here, for instance, you see that the difference image is clean image. So this was subtracted out really well from this, or even this star was subtracted out well from this. You don't see anything here. And this is a very clean difference. Whereas in this case, you see all these objects. So very likely this is bogus. And then you can start. And then there is a field guide, which has greater details available. So ZTF general description, what we are looking for, what are the panels using the light curve for classification, examples of real objects, example of real objects in bad subtraction, example objects with dark pixels nearby, etc. So lots of examples are given there. And then in some cases, you'll find something very interesting. So what you can also do is that not just done, but you can do done and talk. This will take you to some bulletin boards where you can type messages saying that I found something interesting. And maybe others have already found that. So there may be some other information there which you can get to. And then in this panel, you'll find that there are other things. If you go to about, it will tell you details about ZTF itself. So there are a couple of movies there as well. And so one of them is a beautiful movie showing how we change the filters. There is a robotic arm that takes those big filters. If the camera is 47 square degree, right, meaning the filters that we need are going to be big. So this robotic arm goes there, takes it out, puts it in somewhere else, picks up another filter, puts back in, and so on. So quite interesting to see. And then once you have this going, you can start classifying things initially, and then you can discuss these things with others. There are researchers who will be informing you about what is happening, etc. But the interesting thing that think of interest to us would be that if some of you are very keen on this, you can also become administrators of those bulletin boards. So there can be some sections of it in which you are more keenly interested, and then you can take a lead effort in that, and you can start talking with other volunteers. So if you were to form a group, for instance, within your college, then you can start coming in here and getting deeper knowledge of specific kinds of objects. And what we do is that we run different kinds of labs in this. So currently, the campaign that we are running is looking for dippers. What that means is that here what I told you is that we subtract out this reference image from the science image and see if there is a bright new object which will be found in difference image. But we also run the subtraction in the reverse direction. What we also do is we subtract the science image from the reference image and then look for that difference object also. So what is it that we'll see there? The thing that will be of interest is that if there is a star that was present in the reference image but has now vanished or has dimmed a lot, then in this reverse difference we'll be able to see that. And why is that of interest? There are many reasons that could happen. For instance, a star could be fading, it could have vanished, a black hole may have eaten it, or it may have been eclipsed, or there are rarer cases where there are dust shells that are being emitted so that the brightness diminishes for a long time. So we are interested in something like that as well. And the current campaign that's going on is for something like that. But different campaigns go on all the time in here. And then those of you who are interested in programming, the way you can get involved is that as the data get accumulated, as people classify, let's go and classify this one, for instance. To me, what this looks like is that it's going all around. There's nothing. So 0 day is today. So this image was taken here, and these are images from the past. So clearly there's a lot of difference happening here, and similar difference was happening here, and similar difference was happening here. So there's nothing great about today's image. Very likely it's the seeing kind of thing that I mentioned, and you can see that it's very fuzzy here, etc. So I don't think this is a real difference, real good difference here. So I can go and click bogus here and then say done. And when I do that, another image appears here. So here again, I can see that there are two of them here. So very likely this is also a bogus one, though many of the other ones have gone away. So this can be a little bit dicey, but again, the thing to look at is the light curve. So again, today there is this scatter here, but similar scatter was there. And remember, these are several hundred days. So these gaps are the annual gaps. As I said, when an object is in the direction of the sun, you don't get to see it. So this gap is that. So we saw it for a few months, didn't see for a few months, saw it for a few months, didn't see for a few months, and saw it for a few months before, right? So again, I think this is bogus. Let's do that. And many of them could be bogus. This seems interesting. So most of the others are gone away, and it's very likely that it's just variable. So again, because this is something that's brighter in this case and fainter, you can see that there is a bigger distribution here. So again, it's a variable, obviously. So let us say that this is a real object. So if I were to click real, then I get this next. And then I am asked, is it orphan transient? Orphan transient meaning there is nothing seen in the reference image, or vice versa, because this is opposite. Most likely it's a variable. A supernova will be if there is a galaxy nearby, or other will be something else that you know about. So this I'll classify as variable. And when I do that, I click done and I get to see the third object and so on. And there are interesting things that you can do here. You get a little bit more information if you click on this eye, or you can reverse background this so that if you want to see more details there, you can zoom in using this, zoom out using this. You can move things around if you want. So if you zoom in a lot, then you can use this to move around, etc. So those things, the standard things you can do as well. And then the data that people are entering in this fashion goes and sits in a JSON file, which we can download. And then if you are interested in data analyzing that kind of thing, then we can also share that, and we can set up a project related to that. So there are lots of opportunities. So if you simply want to come in and click and provide inputs to science, that is possible for different types of such campaigns. Or if you want to get into more detail and become an administrator, etc., by forming a group and help others, that is also possible. Or if you want to help us classify the objects once the data have been collected and do some machine learning with that, that is also possible. So all these kinds of things are there. So let me now go back to the main presentation again, and then I'll share you links about this, etc. as well. Any questions? Yeah, someone has posted there that the Betelgeuse had dim. Yes. So definitely, that's something that astronomers have been watching with close attention. And so someone has asked why Gaia can only produce 100 observations in a year. Because what it is doing is that it is looking at the entire sky. More than that, the way it takes observations is that it's sending down only 1D observation. So though it is doing the images, the data are astrometrically very accurate. The astrometry that it has, the positions that it has, is more accurate than by orders of magnitude than what we have had before. And so that takes up a lot of, and then it also has the very low resolution spectrum that it's taking, which it's sending down with it. So all that takes up resources. And so at a typical position in 5 years, it's going to observe only about 70 observations. So it's not even 100 observations in a year. It is 100 observations in 5 years. Okay, let us get back to our presentation. Let me share that. Any other questions, by the way?
Sir, there is one question. How do we take more deeper and clearer image of the M87?
For anything, if you want to take deeper and clearer images, you can stack them. So if you take lots of images, then you can put them together and get that. So even with ZTF, we do have deep images. So there is a deep quaded image for lots and lots of things. So the main thing is find dark part of the sky, have good seeing, and then take lots of images and be able to go at those.
There is one more question. Can I subtract science image from reference image?
Yeah, so that is what I was saying, right? For the dippers, that the current program that we are doing right now, that is what is happening. So we are subtracting the science image from the reference image and then looking for objects that have dimmed as well. So objects that become brighter or objects that dim, right? Both of those. So here what we have is, this is the Zooniverse kind of setup that we have. But there is another thing that we are setting up within Zooniverse, which is called the stellar sleuths, looking specifically for classification of variable stars. And here what's going to happen is that we are going to provide how the location of the star is in the Hertzsprung-Russell diagram. So the diagram on the bottom right is the Hertzsprung-Russell diagram. This is where the main sequence objects are. The sun is somewhere here, and we have got dwarf objects here and giants objects here. They branch off from here. And this beautiful diagram that shows you the relationship between temperature and luminosity and different kinds of stars. And many variable stars are periodic variable stars, which means that if you are able to find the period, then you can fold the light curve and get a very regular looking light curve, the folded light curve. So in this particular part of the Zooniverse campaign, what we'll also have is we will have folded light curves that you could yourself make. You can change the period, for instance. You'll be shown how the amplitude of the star was changing, what the period looked like, etc. And using that, you'll be answering a few questions related to variable stars. So that will help us a lot in being able to classify different kinds of variable stars. The third thing that we'll be launching is the Zwicky Chemical Factory, where we'll be trying to classify spectra from supernovae. So completely different project, again, based on ZTF data. So these spectra will be displayed, and spectra, of course, have emission lines and absorption lines, and they have a certain slope, and then how they fall and what kind of, where the emission lines are, that can tell you the redshift. So all those properties are there. You can look at those and be able to classify supernova spectra with those. And of course, we have programs to do that, but many times there are some spectra that are close to some other spectra. And so being able to distinguish that rather than with a program, if our own neural network is looking at that, then that can be a better thing with some expertise and with some practice, for instance. So this is what you'll be shown is an actual spectrum and some fit over it, and then subtraction of it. And these are different kinds of emission lines that are seen and examples of different kinds of spectra. So with each of these three, just like I showed you for the quirky transients, you'll have a tutorial, you'll have a field guide. So you'll be able to look at all those details. And in the talk area, you'll be able to talk to other people, discuss things, ask questions, and that way move along with others as well as with experts. They'll be telling you about lots of these things. So these are three of our programs that are there. And right now the quirky transient is already active, and the other two are coming into picture very soon. So this is the tiny URL that I have created if you wanted to go to the quirky transient one that I showed you. So just go to https://tinyurl.com ZTF sky. That'll take you to the Zooniverse demo there. And you'll need to get a free login from Zooniverse. It's a very straightforward thing, and then you'll be able to log in and be able to classify things. Be sure to read the tutorial first. Be sure to go through the field guide so that you know what's going on and you understand the basics that are involved there. And then after that, you should be ready to start classifying. But again, as I said, the simplest thing is just going there and starting to classify. But you can get involved in the bulletin boards and take ownership, be a leader, and organize your group. And the third level will be where, if you are interested in doing programming, then you should be able to also access data sets from there. For that, you will have to contact us. And then you'll be able to get data sets from there, analyze that using machine learning or some other way, and so on. There are lots of different ways. So they also have Jupyter notebooks that are available, etc., which can be used with that. So one of the campaigns that we currently have are negative subtraction. That is what I said, that we subtract the science image from the reference image. And then it has a real bogus score greater than 0.7, which means that we are already running a machine learning filter that tells us that its probability of being a bogus object is really low. And MAC PSF greater than 17, which means that it is not very bright. It need not be very faint either, but something that seems of interest. And SSDist NR greater than 7 means that there is no solar system object, known solar system object that is within 7 arc seconds of the object. So it's unlikely to be a solar system object. So that is what the campaign currently is. And so I'd like to mention a few tools that are out there. So if you get more interested in doing astronomy, the tools, that has been a big revolution in the last few years. So there is Python 3 out there. If you like programming, there are many libraries available in astronomy. There is Jupyter Lab or Google Colab. Google Colab even allows you to use GPUs and TPUs for free up to 12 hours. So many machine learning workflows you can do for free, for which you had to pay earlier, or even you could not easily find. You can do that quite easily. And within Python 3, there are lots of libraries available like AstroPy, NumPy, Pandas, Scikit-learn, TensorFlow, Keras. These are advanced, so maybe some of you are not you have not heard of these, but if you have heard of these, then this is what you can take and do things with the kind of data sets that I showed you earlier. And it's become really straightforward to do that. And I would really like to encourage you to do that. So earlier, astronomy used to be where you take a telescope, look through the sky, look at maybe meteor showers and some planets and so on. But really, with all this data that we are getting, again, remember 1.4 terabytes every night, right? With all the data that we are getting, there are lots of things that you can be doing with that, not just observing with the telescope. That you should continue doing, by the way, because that is fun. That's really fun. So, and then there are many other online resources also. We have the Caltech course 119, which we are currently teaching. So lectures related to that are online. And then we have a group called International Astroinformatics Association. So you can find more resources there, or there are many data science schools and courses. What the lectures that have been taught there are online. So there's the La Serena School, there's the Growth School, there's the LSST School. And there are also fellowship programs. You can apply for getting admission to that. Currently it's online, of course, but there are also ways you may be able to go and attend those schools also. So keep your eye out for things like these. And I can also email these links to the organizers and they can distribute it to others later on, maybe. That way you can use it later on. So one thing that I wanted to talk again in a minute was how many of the machine learning tools can be black boxy. And one of the things that we are trying to do is go towards explainability, try to make sure that the results that we get from machine learning are something that we can understand and try to bring that in. So decision trees are simple and very explainable, but not very predictive. Whereas as you go to deep learning on the top left, it's the prediction accuracy is great, but sometimes it's not easy to understand what it's telling you. So we are currently have a program where we are trying to understand all these in a better way. So trying to come up with initial features that will help us with that. And so what I'll do is that I'll summarize with this and leave the remaining time for questions and interactive things. So there's a lot of data out there, many detailed tutorials and examples, a lot of possibilities for projects, and lots of citizen science projects as well. But it is quite important to dirty your hands with a little bit of programming, because that really opens up lots of possibilities for you. And then only the sky is the limit, or maybe not even that, right? And again, that's a tiny URL for the website that I mentioned earlier for the Zooniverse thing. And I'll stop with that, but we can take a few questions, I guess. Thank you.
Thank you so much, sir. It was indeed a pleasure listening to you. Now we'll move on to the question. We have, can we use AI technology to get better images and filter them?
Yes, definitely. There are ways to do that also. But right now, so that is something quite difficult because when you are saying that get better images, I suppose what you're saying is that whatever images that have been taken from the Earth with the atmosphere, then the light spreads through the atmosphere and because of the saying, there is a certain FWHM. So you can do things to try to improve that, but that's a non-trivial problem because each pixel is changing somewhat differently. But a lot of that you could simply co-add images and be able to do that. So when you say improve images, it can be taken in many different ways, and there are many possibilities related to that also. But yes, definitely.
Next question, why are some observations of telescope non-uniform, especially the CRT's one? We could expect the universe to be uniform.
Well, as I just now said in the answer to previous question, it is partly because of the atmosphere that the variations come about. The different layers of the atmosphere are at different temperature. So when photons from a source come in, they start shimmering, and you see they spread around in a area, and that is how the images look somewhat different. And that is why, if you remember, what we are taught in school is that stars sparkle, whereas planets, which are extended bodies, they look more solid. They don't seem to vary like stars do. And stars, though they are far bigger than planets, they are also far, far away. And that is why they are like point sources, whereas planets are not like point sources to us. That's again mainly the atmosphere's doing.
Next question, do we use KNN approach to identify celestial objects?
You can, but right now for stars, there have been so many observations from the past that just to identify stars, you won't really need that. But as you go to fainter and fainter magnitudes, as you start trying to identify different kinds of objects, you can use clustering, try to bring together similar types of objects using methods like that.
Next question, is there any virtual telescope website where we can do survey of night sky by operating the view?
I believe there are, and maybe Malhar may tell you a little bit about that. So I'm not up on the latest ones, but yes, there are telescopes of that kind.
Next question, what is the basic difference between science and reference images?
Oh, science and difference image. So science image is an actual image that we have taken. It's a 30-second long image, and the difference image is created by subtracting the reference image from the science image. So you do a point-to-point difference between the two with some modifications, normalizations, of course.
Next question, how will I get job in this field after completing BSc Physics?
Well, you can get a job, depends on what kind of job you want, right? Meaning if you want to do it only after BSc, it will really be good if you do masters and get more involved in a specific area, because then, so in astronomy, there are many different kinds of jobs. There is an astronomer, there's astrophysicists, which are the standard, but these days we also want people who can build instruments. So it is not as if only people who do physics, that theoretical physics, become astrophysicists, but instrumentation is very, very critical to it. Plus, as you just heard me saying, software is also very critical. So good software, machine learning is very important. So if you are in that kind of line as well, you can get jobs. So there's, what kind of job you get depends completely on you. Be open, and there are many, many possibilities, but you have to be good. That's the only thing.
Next question, can we study the period change analysis of CPs and RR Lyrae through this project?
Yes, so the Staler Sluice project that I mentioned will be more appropriate for that. And definitely there, what happens is that we have observations of a very large number of RR Lyrae and Cepheids available, and you can play around with their periods, and you can play around with their light curves, etc., and do lots of interesting things. So in short, yes, you can. So someone has
Next
asked whether
question.
they can do masters in astrophysics after completing bachelor's. Yes, you can, because your bachelor's in engineering is typically 4 years, right? Yeah.
Next question. Should we use data from research paper or database of telescope?
For what, right? Meaning, so both are similar. If you are doing your own observations, then you'll need to calibrate those observations, make sure that you have taken out the signatures of the instruments, and that is perfectly fine to do. So there are two kinds of people who like to observe themselves and people who like to take ready-made data and work on it. Both approaches are perfectly fine.
Next question. How can we study the atmosphere of exoplanet? Any techniques or scientific approach to analyze and detect presence of gases?
Present of?
Gases.
So, so exoplanets, the interesting thing about exoplanets is that planets are tiny and the star is typically much brighter, right? So you have to remove the light of the star to be able to properly observe the exoplanet. Otherwise, whatever observations that you take are likely to be dominated by the stellar light. So there are many techniques. There are techniques, for instance, in which you can hide the main part of the sky, a star, and when the planet, especially if it is a face-on orbit, then you'll be able to see it when it's away from the star, etc. And then if you take a spectrum of it, maybe you can get the spectrum. But there are also indirect methods like radial velocity and using the temperature of the uh, star, etc. You can do lots of things related to that. I am not an expert in exoplanets, so I do not have the specific answer to how to detect specific gases on exoplanets, but I know that people have techniques to do that.
Next question. What do you think about ARC reactor, electromagnet?
I'm not sure what that means.
Move on to next question. Sir, what are the prospects of astrobiology?
Yeah, so astrobiology is an area which tries to study if the life on planet Earth came from some other area. But I personally feel that that's just pushing the question that we have here to somewhere else, because life has to originate somewhere. So why not on Earth? So I personally feel that it could have evolved in many, many places, including the Earth. But then there could be some thing that comets did bring. Comets do have water. They do bring water, transport it in different parts of the solar system. So there may be something to that. And the more interesting thing currently is the planetary protection kind of thing. So at JPL, which is a part of Caltech, we have something called a Planetary Protection Agency. Just like at NASA, there is, and JPL is also part of NASA. So there, the main thing that they're trying to do, and that's connected to astrobiology, and that's why I'm bringing this up, is that when we launch something and land on another body like Moon or Mars or wherever, or some moon of, say, Jupiter or Saturn, then many times we are looking for life there. That's one of the main aims of going there also, besides seeing whether it's livable for us. So the worry is that we should not be taking life from here and putting it there and discovering it there after that, right? But how do you know when you take spacecraft? There will be bacteria or viruses that may go with that and so on. So the Planetary Protection Agency is worried about that, and they try to come up with protocols to make sure that we'll have clean rooms and we won't take any contaminants from here to there. So astrobiology is also partly related to that. And that is an area where I think there is definitely a lot of scope.
Next question. If a star is orbiting in a binary system, will it be possible to tell exactly the characters of the two, or it will be an interference of both?
So it depends on how close those are, what their temperatures are and colors are. But now we have been studying them for a long time, so we have gotten very good at being able to tell them apart quite well. So, for instance, there are many kinds of binary stars that have been studied really, really well. So, in general, the answer is that we can tell them apart quite well. Characteristics of both. Yeah.
Next question. What do you think about the parallel universe?
I also write science fiction, and I think it's a great idea. So, but how will you observe them, right? Meaning In physics, in astronomy, one of the main things for most theories is you should be able to predict something that can be measured. And if you can't do that, then you can have any kinds of theories. And then that's like Russell's teapot. So Russell made this comment that if I tell you that I have a teapot that goes around the sun between, say, Earth and Mars, but it is too small to be observed by a telescope, then you cannot contradict that. And so you cannot prove that it doesn't exist, for instance, right? At least for now, parallel universes are something like that. So if it's going on and it's doing something, sure, it could be doing. But unless I have an observable, unless there is a way for me to say that it does exist, or at least refute its existence, either way, then it's fiction or fantasy until then.
Is, sir, you mentioned about data release 3 by ZTF example query using APIs. So can amateur explore something meaningful out of it?
Oh, absolutely. And right now we already have data release 5, by the way. So what the API does is that these are programs that you have available. You can download the URLs that I had shown there. You can use those URLs from your browser or from your command line to access the data release, and you can ask for portions of those catalogs. So you can ask, for instance, that ZTF, the brightest object ZTF observes is 12 to 14th magnitude or so. Above that, everything saturates. So if you wanted to observe with a small telescope, then you cannot really get 8th or 9th magnitude objects with that. But suppose you had a slightly bigger telescope. Say you had a 24-inch telescope and you wanted to observe something with that. You could ask, give me everything up to 16th magnitude in this part of the sky, and you could get that back. Or if you want to do theoretical studies, then you could ask for all RR Lyrae or all Cepheid. Someone was asking questions related to that in a given area of the sky. And you can get the entire light curves for those sky. And then you can analyze it on your computer to your heart's will.
Next question is, if I learn Python, then what are the jobs and what is the process?
So if you just learn Python, then software, right? But if you're talking about astronomy, you'll have to learn about some additional astronomy libraries also. And then you'll have to dirty your hands with some data. And so these days, again, things like GitHub and so on, they are great. You can start projects. You can look at projects that other people have written, form teams, start pushing out code. You can get visibility that way. And if you're doing it well, then people will notice you. So there are many virtual conferences these days where you can apply. So in India, the Astronomical Society of India meetings used to be once every 2 years, but now they are annual. And they have been encouraging more younger students to participate. So that's definitely an avenue to look at. Those are annual meetings, so that would be the best avenue, I would say.
Next is, Sir Stephen Hawking once said that the God creation theory is just a story tale, and also said that asking the question, what is before the Big Bang, is just searching the north on the North Pole. What do you
So
think about it?
I think we are starting to get into philosophy. Let's try to stick to the topic of the talk and get into that.
Okay, next question is, age of the universe we
Similar.
know.
So
Yeah. Can we have any technique to have a glimpse of the dark matter as it is only interact with
same.
only yeah.
I'm going to skip that.
uh, Next is, what are the aspects in astronomy and astrophysics after mechanical
So again,
engineering degree?
mechanical engineering degree, I would say, is connected to instrumentation. You don't have to be an instrumentation engineer to do that because there are many mechanical related things as well that are involved. Consider the LIGO Observatory, and India is hiring big in gravitational wave astronomy right now, but not just theoretical one, but the observatory is going to be built. And in fact, it is going to be built in Maharashtra, not far from Hingoli. And they are going to need a large number of people in all fields, essentially. Similarly, India is part of the GMRT and a couple of, not GMRT, yes, but also TMT. And there are going to be other projects that are in India related to astronomy. So no matter what science you are in, what engineering you are in, there would be ways to get involved.
Is that all the questions.
Well, I hope you enjoyed, and I can provide some of the URLs that I mentioned to the organizers, and then they can maybe share them later on.
So gratitude is one of the least articulate of emotions, especially when it is deep. Today, I take the opportunity to put my gratitude in words. On behalf of Astronomy Club, Government College of Engineering Nagpur, Stargaze Committee, and all the participants, I would like to extend my heartiest thanks to our honorable guest speaker, Professor Ashish Mahabal sir, for enlightening us with your inspiring and motivating words. You are an exemplary person, and we have a lot to learn from you, sir.
Thank you for inviting me, and next time, hopefully, this can be in person. So
Yes,
next
sure.
time I visit Nagpur, which used to happen every 6 to 8 months, but I haven't been there
Yeah.
for the last year and a half, obviously. But at the first opportunity, I'm going to get back there, and at that time, maybe we can have a meeting in person, perhaps.
Sure, sir. Yes. So moving on. I'm really honored to welcome our next guest speaker, Mr. Malhar Kendurkar sir, an observational astrophysics researcher based in Prince George, BC, Canada. Currently is working as president of Prince George Astronomical Society, Royal Astronomical Society of Canada, and as a past director for 4 years and a principal investigator of Global Supernova Search Team. Malhar sir is also an instructor of physics and astronomy at IUCAA College of Vancouver, BC, Canada. He is the first person in the history of Canada to search for more than 90 supernova in a year. An investment in knowledge pays the best interest. I would like to invite Mr. Malhar Kendurkar sir to share his knowledge and experiences with us. Over to you, sir.
Thank you so much for inviting me in this wonderful workshop. And I have, you know, if there was no COVID, it would be a wonderful opportunity to come to the college in Nagpur. For the past 6 years, I haven't actually been in India because it has been, um, busy and my education. But I'm really looking forward to deliver my presentation for today. I'm just trying to share the screen here. One second. For some reason, I can't share my screen. Okay, here we go. Let me know if you guys can see the screen.
It is not visible, sir. It's a black screen.
Uh-oh. Okay, one second. Okay. Is it visible or?
It's the same problem as before, like before the start of the session.
Uh-oh. Okay, should work now. Okay. Okay, can you guys see it? Okay, so I'm Malhar. I'm living in Prince George, Northern British Columbia, in Canada. So, in today's presentation, I'm going to talk about Global Supernova Search Team. So, it's a Supernova Search Team which was founded in Canada, and we are, similar like ZTF, but in a very small capacity. We are trying to look for transients in the sky. So, and I'll give you a brief overview of what Global Supernova Search Team is. So it's the first sky survey in Canada dedicated to search for astronomical transients. And it was formed in 2018 with 2 astronomers from Canada and 1 from France, with the same goal of searching supernova. And we are, using very moderate equipments. We don't have, we are using several different instruments to search for astronomical transients. And we have instruments scattered all over different part of the world. So in the first 2 years, we tried to scan the entire northern hemisphere, and I'm located at 53 degrees north. So it's we are really high up in north. So in Prince George, because we live in the north, we don't have a lot of clear nights here. We usually get around 100 or 120 in a year, which is not a lot for for sky surveys. And in 2019, we had five people in GSNST from United States, India, and Argentina. And from India, we have Rohit, who works really hard for the team, and he is doing a wonderful job. And some amateur astronomers from United States. So basically, GSNST is a team of amateur astronomers who have their own equipments, from 12-inch telescope to 24-inch telescope. And some of our members also have spectrographs, which we use to do the classifications of the supernovas and also variable stars. We also heavily study variable stars, northern variable stars, only in north. But we are, as we get more time on telescope and we get more people who wants to study more variable stars and, transient, will try to search for variable stars using our archival data. One second. Sorry. Okay. And in 2020, last year, our GSNST team became an all-sky survey so we are covering both northern and southern hemisphere. So we have telescope in Argentina, which is covering southern hemisphere, and we also use SLU observatories, which is a robotic telescope located in Chile and in Canary Islands, which is in Spain. So using those 2 telescopes, we are covering a lot of southern hemisphere as well. And in northern hemisphere, we have a lot of telescopes. So from Prince George to Arizona, we have in total 6 instruments which are covering north. And in 2020, we have 11 members from all different countries, from Canada, France, India, United States, Argentina, and UK. So we actually got one collaboration this morning from United Kingdom. So he's actually one of the leading spectroscopist in amateur astronomy community. He has classified over, I think, 100 supernova discoveries from all different surveys. So why do we survey the sky? We have all these wonderful sky surveys which are scanning the skies every day, every possible clear night. So we are surveying the sky to search for astronomical transients such as novae, supernovae, optical counterparts of gamma ray burst, and also gravitational waves. Also, to know the intrinsic and extrinsic details of any astronomical object we are looking for, from variable stars to largest explosion in our universe, which are supernovae, gamma ray burst, kilonovas, etc. So, in contrast, most people think, astronomers point. So the surveys works differently. We don't point our telescope at the same spot every night. We scan the entire sky. So we are looking for, the skies are very violent things. So there are very objects which are exploding, massive explosions like supernova. So that's why we scan a lot of galaxies every night. So right now we are scanning about 100 to 150 galaxies each night to search for a supernova. But our supernova discovery rate is not extremely high right now because our limiting magnitude for some of the telescope is only 18 magnitude in 50 seconds exposure. And the bigger telescopes we have here in northern British Columbia, which is our 24-inch telescope, so we can go down to magnitude 21.5 in 300 to 500 seconds exposure. And by finding and studying some of the supernova deepens our understanding of formation and expansion of the universe. So how does GSNST survey the sky? We are using several different instruments. So this is one of our main telescope. We started doing the sky survey. So this is located in Prince George. And we have a wide field survey camera mounted on a 0.6 meter telescope as a part of GSNST. And using Prince George Observatory, we are scanning the entire night, northern sky, northern hemisphere 6 times each night. And so far, using this telescope, we have discovered 17 supernovas and 3 novae in Andromeda Galaxy. And limiting magnitude of 24-inch telescope is 21 magnitude in clear filter. So all of our transients, all of our survey we are doing, it's all in clear filter. Other main telescope we are using to survey the sky, one is in northern Spain, and this is in southwest France. And we also use SLU robotic telescopes. So there was one question I remember one person was asking, are there any robotic telescope to use? So yes, you can use SLU robotic telescopes to scan the skies, but there are limitations in using these kind of robotic telescope because they allow you to use only 25 minutes each night. So that's not a lot of time to survey the sky. And we use SLU observatories occasionally. But as we're having more and more telescope, more and more collaboration with GSNST, we are having more and more telescopes. This it's a half-meter telescope in Arizona Sky Village, and this is another half-meter telescope in Osoyoos, British Columbia. And we got a couple more new collaborations who wanted to be a part of GSNST from Canada. One is in Montmégantic, Quebec, in Canada. And another robotic telescope, which is in Benson, Arizona. And that our telescope in Arizona, in Benson, is very, very active to search for supernovas and to study the variable stars. And the last but not least is another one in Frontenac, Quebec, in Canada as well. So these are all the location of our observatories around the world. And so we are pretty much scanning, a lot of northern sky right now, and also southern sky, but we need to increase our rate of scanning the southern sky and northern sky to find some faint astronomical transients, faint supernovas. So this is the sky coverage of GSNST. So we have 24-inch Prince George Astronomical Observatory, and which is called PG24. And then we have two telescopes in Spain, which is a 17-inch telescope, and they have CCD cameras. And we have a couple telescopes in Argentina, which are scanning the southern sky, and one telescope in Chile. So since 2018, we have monitored around 14,000 galaxies in north and in south. And so far we have discovered 137 supernovas. So we are continuously, scanning northern and southern hemisphere every 6 days, but mostly because of weather challenges and seeing conditions, it's really hard to find the transients. And there we have a lot of surveys these days, for example, Assassin, ZTF. And it's so the sad part about SLU observatories, so if we find any transient, we have to wait for 24 hours to data to come through our systems. So if there are any transients, other surveys usually report bright transients. And from north, we usually can go down to magnitude 22 in 300 seconds exposure with our 24-inch and couple half-meter telescopes we have. For spectroscopy, we currently have only two spectrographs. One of our spectrograph is in Montmégantic, Quebec, and one is in United Kingdom. So the limiting magnitude for spectroscopy is only 18 for us for now, because we have very moderate equipment to do spectroscopy of high magnitude supernovas. And these are some of our discoveries made by our team members of GSNST. We still have to add a lot of discoveries in here. This is not updated. So as we can see here, we have discoveries both in north and in south as well. So from early science results, this is one of our discovery made last year in 2020. This was a type 1A supernova in NGC 5157. And then we have another supernova in SDSS galaxy, which was identified as type 1A. And we have another type 2 supernova discovery in Dark Energy Survey galaxy. And we also captured optical flare of a quasar last year. Apart from discovering the supernovas, we also study variable stars from eclipsing binary stars and all sorts of variable stars. We have discovered and reported quite a few delta Scuti type stars and eclipsing binary star, contact binary stars. And we are also doing work on luminosity ratio of variable stars, getting the spectroscopic observations of variable star to identify the radial velocity, O minus C curves, etc. So after finding a possible transient, we reported to the transient name server, where all the sky surveys, including ZTF, reports their discoveries. So GSNST usually reports all the discoveries manually, and there are automatic reports goes through the TNS, for example ZTF, and there are different kind of events, alerts you can find on ZTF, for example, transients, AT, and then we have classification of supernovas. So you can see all the classification from type 1A to type 2A for type 2, and then we have fast radio burst, gravitational wave events, and astronauts. If there are any special supernova events, for example, a TDE, tidal disruption event, or optical counterparts of gamma ray burst, you can find everything on TNS, and it is publicly available. So this is a chart of GSNST since 2018 to 2020. Blue ones are the GSNST discoveries, and the red one are false positive, which have not been reported to transient name server. So as we started scanning more and more, our discovery rate actually went higher and higher. So we are hoping to discover at least 200 supernovas this year using all the equipments we have. So today, GSNST, so we are developing an automated, transient search pipeline. One of our member, he is developing the pipeline, and then another thing we are working on, we are building our own GSNST server. For 2020, we have discovered 43 supernovas so far. And the discovery target for 2021 is around 200. And now that we have new team members from different parts of the continent, so we are also scanning. Now we are officially an all sky survey. Also, we took a next step for GSNST, that we are looking for research grants to build 6 robotic telescopes in northern British Columbia to advance our search for supernovas and gamma ray burst. And these GSNST observatories will be the first observatory in Canada to do this kind of work. Here's our workflow of GSNST. So we schedule the time on our observatories. Then we get the target object and CCD output, meaning the fixed files. And then we do the image reduction and then image subtraction. And if there is a new possible supernova or any transient, we go for at least three follow-ups before reporting to TNS and astronomers' telegram. So that's how, if we get the grants, that's how our telescopes will look, and each telescope will be 17-inch telescope, and 1 out of 6 telescope, 1 telescope will be for rapid follow-up observations of any astronomical event. Alerts from ZTF, from LSST, Atlas, Assassin, and or any other sky survey. So in summary, we are progressively survey the sky in both northern and southern hemisphere, hoping to discover rare supernovas in our night sky. And by discovering new type of supernova, it might give us information that we don't know about our universe yet. Also, maybe end of this year, we will make all of our data publicly available from both hemispheres. So this data will be useful to study variable stars, times of minima, O-C curves, and radial velocities of different type of variable stars. And some of anyone can take part in this kind of search, and they can find their own variable stars too. Any questions?
Yes, sir, there are in the chat box. Why do supernova occur in the vicinity of a galaxy?
Good question. Well, what type of supernova? There are type 1a supernova and type 2 supernova. So type 1a supernova happens when there are two stars. One is a white dwarf and one is from a red giant to, white dwarf. And when a white dwarf sucks all the matter from the red dwarf, red giant star, it cannot withstand its own gravitational field, and it explodes in a supernova. Okay, and for type 2, for type 2 supernova, it is called a core collapse supernova, which usually happens when all the matter goes in the core of the star and the star gets too heavy, and it explodes in an explosion. So that's a type 2 supernova, and it usually happens in the arms of a spiral galaxy. You can see, for example, it was a type 1a supernova, which was happening in NGC 6946 in 2017. One of the amateur discovered, and that supernova was very interesting. It was actually visible for almost six months. So they can happen, supernova can occur anywhere in any galaxy, like in any part of the galaxy.
Next question is, what is the workflow of GSNST?
What? Pardon me?
Workflow of GSNST
Workflow?
of GSNST.
Okay. So workflow of GSNST. So we, schedule the galaxy and the targets which we want to observe the night before our survey, before we start our sky survey. And depending if the skies are clear, where we have our telescopes. And after getting all of our data, it goes on the computer I have in our office. And then I usually send all the data to everyone. We have, we use application to use that. And then our team members scan that data manually. We don't have anything automated as of now. We are looking everything using our eyeballs. So we are literally staring at the computer for hours to search for supernovas. So after getting that data, we scan the data, and if there is a possible transient we saw or a supernova, if we see it, then we will try to take follow-up from different locations. And if we see that transient again on our new CCD chip, then we will report the transient and wait for the classification.
Next question. How do you discard false positive in observation?
Okay, so we reduce all the data and then we do the image subtraction. So it gets rid of all the bad pixel, hot pixels, and all the false positive and noise.
Next question. Can you elaborate more on SN 2018 COW?
Can I elaborate more on, pardon?
SN 2018 COW.
Oh, SN 2018 cow. I did not study that supernova. I know that was a interesting type of supernova, but I I didn't look at that supernova a lot, so I didn't really read about that supernova like a lot. If Ashish sir know about that supernova, he can maybe answer that one.
So what was the exact question?
Elaborate more about the SN 2018 COW, which was discovered by Atlas, I think.
Yeah, and ZTF also did take observations for
ZTF,
that.
yeah.
Yeah. So yeah, I can put a few references to a couple of papers to that actually. So I myself don't study supernovae, but it was an unusual thing. It was a fast one, and the way its a light curve evolved was quite unusual, and it seemed a class in itself. And more recently, we found another one, and because of the cow, people are trying to find. So ZTF, the nomenclature is such that you have the 2018, 2019, and then there are 6 or 7 alphabets. So sequentially they are named, and then people start finding patterns in that. So the new one is camel, for instance, just like cow, there is camel. So you should look out for camel as well. So
Okay, I think that are all the questions.
Thank you. I have one personal question from Pradeep. Can we get CCD images of Cepheid and RR Lyrae pulsating stars? Yes, we can. Yes, you have to take long time series on the stars, depending on the what is the period of the star. Some of the stars we have observed and discovered, they have a period of 2.5 hours. From alcohol type stars have period of days sometimes. So yes, we can get CCD images of Cepheid variables and RR Lyrae pulsating stars.
I have one question.
Is
Is
GSNST?
GSNST planning to use X-ray, flash radio, telescopes, etc.?
No, GSNST is an optical sky survey, so we don't use any radio telescopes or X-ray telescopes to do any kind of sort of observations. We are only pure optical sky survey and clear filter.
We are done with the questions now.
Okay.
So, wholeheartedly, I would like to thank our honorable guest speaker, Mr. Malhar Kendurkar, sir, on behalf of entire Astronomy Club of Government College of Engineering, Nagpur, Stargaze Committee, and all the participants. Thank you so much, sir, for your efforts and taking out time from your busy schedule and gracing us with your knowledge.
Thank you so much for having me. It was a pleasure.
The larger the island of knowledge, the longer the shoreline. This event would not have been possible without the guidance and support of Dr. J.B. Randhawa, ma'am. So I would like to request ma'am to say a few words on this occasion. We have some connectivity issue.
Okay. No, there's no connectivity issue. Actually, it was on mute.
Okay.
Yeah, the mute was locked. Therefore, I could not speak anything. Anyways, now I'm audible to you all, I suppose. And
Yes, ma'am.
it's been a pleasure to have Ashish Mahabal sir on this occasion again. And also Mandar Kendurkar, who has been there in our astronomy club WhatsApp group since years, and we have been constantly getting about the updates of his achievements and all those things, and he has been guiding to our students of the group also. So it's been really a great thing that both of you have joined, and you are keeping your association with our astronomy club. And I am not a person of astronomy, so I have very little to say on this, but I have listened to both the sessions, and they are really wonderful. They have Mahavar sir has shared very technical tips related to the having a good career in the field of astronomy and astrophysics, and it is really very much beneficial to all our students. Thank you very much, Mahabar sir and Kendurkar sir also. And we solicit same sort of cooperation from both of you in due course of time. Thanks are also due to Rohit, who has continued our association with the Astronomy Club since he has started this club, and he's continuing with that. Thank you very much. And also the all astronomy club students who are taking all labors to continue this particular club ahead, and every year we are adding a few more good activities. Now, as we have gone online, we have gone to the level of national level, and we have now contributions coming for our competitions all over India. So it's really good, and I see very great going for this club also. Thank you very much, all of you. Over to you,
Hello.
Palak.
Hello. Hello. Hello.
Yes, Pradeep, you are audible.
Yes. Yes. Can I say something to Malhar sir?
Yes, sure.
Okay. So I am Pradeep Karmakar from Calcutta. I am very much interested in the field of variable star. Okay. And I am doing some work uh, on period change analysis of Cepheid. Okay. So after listening your lecture, I am very much eager to do, if there is any possibility to do some project on the same type of analysis like CCD, sorry, Cepheid period change analysis using O minus C techniques. So if there is any possibility to get the CCD images of either Cepheids or RR Lyra through from your observatory, then I shall try my best to reduce the science data set using V-Fort or Dow-Fort. Okay.
Yeah.
So is there any possibility? I'm very much
Absolutely.
excited to.
Absolutely, yes, there is. We have, a lot of data which needs to be analyzed of Cepheid variables and RR Lyra data too. So if you want, you can do a project, and I can provide you the data for that. So I'll give you my email address, so we can actually have a conversation about this. And
Okay.
so it would be actually wonderful.
Okay, it's very pleasure to talk with you, and if I get this type of chance to do some work with you, and that will be a very great thing to you. Okay,
Absolutely.
so So how can I communicate through you? Could you please send me your email ID,
Yes.
or
I'll send
you
you my
can?
email ID. Oh, sorry. Oh, go ahead, please.
Okay, folks, I need to leave. It was a pleasure being here. So talk to you again soon, some point somewhere. Bye.
Okay, okay. Thank you. Thank you.
Thank you so
Good
much,
night.
sir.
Do you know how can I send a message here? I can't. Pradeep, I can send you my email ID, but
You can type on the chat box.
I can't see the chat box on my screen. I
Oh,
only
it's
see
over
the.
there. It's not.
Oh, here we go. Okay. Okay.